Welcome to Chemistry for 10 plus 2. Dear students, if you like this video, then subscribe my channel, like it and share it with your friends. Let's begin. Today we are going to deal with chemical properties of alcohols and phenols. In this, first we are going to see laboratory tests of alcohols and phenols, in which first we are going to see litmus test, then reaction with bases, characteristic tests of phenols, distinguishing test of alcohols, especially Lucas reagent test. Then we are going to see reactions involving breaking of OH bond, in which first we are going to see acidic character of alcohols and phenols, and then esterification. So let's begin with laboratory test of alcohols and phenols. First, litmus test. At the end, we are going to see acetyl derivatives also. Let's talk about laboratory tests of alcohols and phenols. Here, these are alcohols and phenols. When we talk about litmus test, actually, alcohols are neutral in nature and phenols are acidic in nature. Let's talk about litmus test. Alcohols do not have effect on litmus paper, whereas phenols can change blue litmus red. Let's see the test. In this video, we find alcohols do not have any effect on litmus paper. Blue litmus remains blue, whereas when we talk about phenols, the blue litmus paper turns red, as it can be seen here. Now we are going to see reaction with bases. Phenols react with aqueous NaOH to form water-soluble sodium phenoxide and regenerated on acidification with HCl. How the reaction is taking place? Let's see. This is phenols. When it is treated with aqueous NaOH, we find the highlighted part is removed as water molecule, and this Na gets bonded to the oxygen atom, as it can be seen here, to form sodium phenoxide. Now we are going to see characteristic test of phenols. Phenols develop characteristic deep coloration, purple, violet, green, color of ferric phenoxide when treated with neutral FeCl3 solution. As you can see here, phenols plus FeCl3 neutral, it gives ferric phenoxide, which is showing deep color. Now we are going to see the distinguishing test of alcohols, Lucas test. Primary alcohols react with Lucas reagent very slowly to form alkyl chlorides. Ethanol is a primary alcohol. When it is treated with HCl, in the presence of anhydrous ZnCl2, On heating, water molecule is removed and Cl forms bond with this carbon atom to give chloroethane, and water is removed. Chloroethane is immiscible in Lucas reagent. Therefore, two distinct layers are observed, but it requires long time and needs heating. Primary alcohols on heating with Lucas reagent reacts very slowly to give chloroethane. Let's see the reaction with secondary alcohols. Secondary alcohols react with Lucas reagent much faster to form alkyl chlorides as compared to primary alcohols. This is a secondary alcohol, propan-2-ol. When it is treated with HCl, in the presence of ZnCl2 anhydrous, at room temperature, water molecule is removed and Cl forms bond with this carbon atom to form 2-chloropropane, and water is removed. 2-chloropropane is immiscible in Lucas reagent. So, two distinct layers are observed in the solution after few minutes. Propan-2-ol, that is secondary alcohol, reacts with Lucas reagent faster than primary alcohols to give 2-chloropropane. Now we are going to see the test with tertiary alcohols. Tertiary alcohols reacts instantaneously with Lucas reagent at room temperature. 2-methyl propan-2-ol is a tertiary alcohol. When it is treated with HCl at room temperature, water molecule is removed and Cl forms bond with this carbon atom to form 2-chloro-2-methylpropane, and water molecule is removed. 2-chloro-2-methylpropane is immiscible in Lucas reagent. Two distinct layers are observed in the solution instantly. 2-methyl-propan-2-ol, that is tertiary alcohol, reacts with Lucas reagent at room temperature to give 2-chloro-2-methylpropane. Let's talk about Lucas test. students. Now we are going to see the distinguishing test of alcohol on the single chart. Let's understand how it is. Lucas reagent test with primary, secondary and tertiary alcohols. Let's see the reaction of Lucas reagent with alcohols showing distinct appearance of turbidity in the solution. Lucas reagent is the combination or mixture of concentrated HCl plus ZnCl2 anhydrous. Primary alcohols with Lucas reagent shows no turbidity at room temperature. It needs heating and it takes long time for the turbidity to appear. In case of secondary alcohols, turbidity appears within 5 minutes. Whereas in tertiary alcohols, turbidity appears immediately. Let's begin with reactions due to breaking of OH bond. First, we are going to see acidic character of alcohols and phenols. Here, this is the primary alcohol, ethyl alcohol, C2H5OH. When it is treated with HOH, we find hydrogen atom of ethyl alcohol is donated to HOH, that is water, giving rise to the conjugate base C2H5O and H3O plus ions are obtained. In this reaction, electron donating inductive effect of alkyl group destabilizes the alkoxide ion, that is conjugate base of alcohol. As a result, alcohol do not ionize much in water and behaves like neutral in acidic medium. Now we are going to see acidity of phenols. Ionization of phenols can be represented by the equilibrium as shown below. This is phenol plus HOH hydrogen atom of OH group from phenol is donated to HOH to form phenoxide ion plus H3O plus ions are obtained. Let's understand the difference in between alcohols and phenols and acidity. In alcohols, OH group is attached to sp3 hybridized carbon atom, while in phenols it is attached to sp2 hybridized carbon atom. In alkoxide ion, negative charge is localized on oxygen atom. When we talk about phenols, here we find as the hydrogen atom of phenol is removed, there are 3 lone pairs on oxygen atom, giving rise to phenoxide ion with oxygen atom negatively charged. This one of the electron pair moves here, gives rise to double bond character in between the sp2 hybridized carbon atom and the oxygen atom. Since the electron density increases here, this double bond breaks and the electron moves at ortho position giving rise to negative charge to this carbon atom. Thus, the second resonating structure is obtained. Likewise, this electron pair moves here, and as the electron density increases, this double bond breaks and the electron goes on this para position of this carbon atom, giving rise to negative charge. And thus, third resonating structure is obtained. This negative charge now moves here as there is lacking of electrons. As soon as the electron moves here, electron density on this here is increased. So this double bond breaks and the electron moves to this carbon atom, as it is shown here, which gives rise to the fourth resonating structure. The electrons on this carbon atom now moves here, and as soon as the electron density is increased over here, this double bond breaks and the electron moves to the oxygen atom back, giving the negative charge to this oxygen atom. Thus, 5 resonating structures are obtained. While here we find in phenoxide ion, the negative charge is delocalized over ortho and para positions of the aromatic ring. As it can be seen here, this is ortho position, this is para position, this is ortho position. This delocalization of negative charge makes phenoxide ion, the conjugate base of phenol, more stable. Thus, phenol ionizes in aqueous medium to moderate extent, showing weak acidic character. Let's see the reaction involving breaking of OH bond. Let's talk about esterification. Esters are obtained when alcohols react with acid anhydrides. This is acid anhydride plus ROH is alcohol. Acid anhydride reacts with alcohols in the presence of concentrated acid to form the product in such a way as it can be seen here. Esters are formed. Plus RC double bond O and OH will give you carboxylic acid. Thus, acid anhydride, when treated with alcohol in the presence of concentrated acid, gives rise to formation of ester and carboxylic acid. Let's see the example. This is acid anhydride. When it is treated with ethanol, that is alcohol, in the presence of concentrated sulfuric acid, it first forms ester, that is CH3COO C2H5, and OH of alcohol joins here to form carboxylic acid, that is acetic acid. Esters are obtained when alcohols react with acid chlorides. Let's see how. RC double bond O single bond Cl is acid chloride. When it is treated with alcohols, the reaction takes place in the presence of the base, that is pyridine. As shown here, HCl is removed and oxygen gets bonded to this carbon atom to form ester. As shown here, and HCl is removed. Pyridine, which is acting as a base, neutralizes the HCl formed, and thus the reaction is forward reaction. Let's see the example. Acetyl chloride CH3COCl, when treated with ethanol C2H5OH in the presence of pyridine, that is base, the highlighted part HCl is removed and oxygen of C2H5 forms bond with carbon atom, giving rise to formation of ethyl acetate, that is ester, plus HCl is removed. Pyridine neutralizes acid, that is HCl, formed during the reaction. Let's talk about acetyl derivatives. Here, this is salicylic acid. When salicylic acid is treated with acetic anhydride in the presence of acid, we find here benzene ring with COOH and oxygen atom is moved here, and this acetyl group gets bonded to this oxygen atom to form acetyl salicylic acid. Or it is also said to be aspirin. In addition to this, the remaining part, that is CH3COOH, gives rise to the formation of acetic acid. The number of alcoholic or phenolic groups in the given compound can be deduced from the number of acetyl groups introduced in it as a result of acetylation. The CH3CO group is called acetyl group. The acetate esters of alcohols or phenols are also called acetyl derivatives of alcohols or phenols. Aspirin is a well-known generic medicine, is an acetyl derivative of salicylic acid, formed by its acetylation using acetic anhydride. That's all for this module. Subscribe the channel, like it, and share it with your friends. Hit the bell icon to get the notification of the latest update. Goodbye for now and take care.